Any discussion of numerical analysis has to start with a conversation about how computers manage numbers, since they do this in a way that's just very different from the way people do, and that directly impacts the way that computers do arithmetic. So, to a human, we can think of this expression here in an abstract way as the unique infinite digit decimal number that, when you multiply it by itself, gives you 2. Now, for computers to do computations, they have to start by translating this expression into a decimal number with a finite number of digits. Right, so that means that the only numbers a computer can work with exactly are rational numbers. And as we'll see, not even all of those. Every other number has to be represented as one from that finite set. Now, the difference between the actual infinite decimal representation of a number and the finite approximate version is what we call round-off error. Most of the time, this round-off error isn't going to be a significant issue, but there are situations when you're doing arithmetic where this error can get magnified and give results that are significantly off. So in this lecture, what we're going to do is we're going to start a discussion of how to identify and manage these errors. So the Institute for Electrical and Electronic Engineers is called IEEE. Is a professional nonprofit organization that's focused on electrical engineering, electronics, and other related subjects. Among their many activities, they define a wide variety of discipline-specific standards. Now, in 1985, they published the Binary Floating Point Arithmetic Standard 754-1985. It was updated in 2008, and what it does is it defines how binary numbers are defined at various levels of precision. Now, most computers today use binary arithmetic, so that's what we're going to focus on. But just historically, other bases have also been used as well. For example, IBM mainframes used a hexadecimal system, and there was a short-lived attempt to use base 3 by some Russian computers. So our focus is also going to be on what are called 64-bit operating systems, right? Also very common today. And what these systems do is they organize data in 64-bit chunks. Right? So that means that a computer has a maximum of 64 bits, that is 64 zeros and ones, that it can use to represent a single number. So the most brute force way to do this is just take these 64 digits and call it a binary number, 64 zeros and ones. And if we do that, we end up with an awful lot of numbers, right? We end up with this many possible values, and that's great because obviously we want to have as many numbers as we can. The problem is they are strictly positive integers. Right? There's no way there would be no way to do negative numbers, and there would be no way to do decimal values. And in some scenarios, that's okay. There's some programming language that have a variable type called an unsigned integer that does exactly this, and it has this enormous range, and that's great. But we need to be able to do negative numbers, and we need to be able to do decimals, right? So here's how we're going to do that. And I know there's a lot going on here, right? So just kind of bear with me. We'll unpack all the pieces here and see how we turn these 64 bits into a decimal number. So the first thing we're going to do is we're going to use this first digit here just to represent the sign of the number. And so if that first digit is a 0, the number is positive. If it's 1, the number is negative. And you see that represented in this part of our little formula here, right? S is the exponent of that -1, and that's going to determine our number sign. Now, the next thing we're going to do is we're going to define what's called the exponent, or the characteristic. And the way we do this is we take the next 11 digits. Remember, this is a binary number here, right? And we turn that into our exponent. We're going to do it in a very special sort of way. Okay, so first, there's 11 digits here, which means we have 2 to the 11th minus 1 possible numbers that we can get from this. 2 to the 11th, that's 2048 minus 1. That's 2047 digits. Now, we could just let that be a power of 2 when you see where we're going with that down here in the formula. But that would give us a lot more big numbers than it would small numbers. Okay, so what we're going to do is we're going to take the number that we get from this characteristic. We're going to subtract 1,023. Notice that's just about half of this, right? We're going to subtract 1,023 from it, and that's going to be the exponent. Right, so what that's going to do is it's going to give us a range of both positive and negative exponents. So we're going to be able to represent large numbers, numbers with large magnitude, with the positive exponents, numbers with small magnitude, with the negative exponents. And another thing I want to point out here is, remember, this is a binary number we're talking about. And with decimal numbers, think about what the effect of multiplying by a power of 10 is. Right? You see this all the time when you first start learning about scientific notation in the metric system, for example. Multiplying by a power of 10 has the effect of moving the decimal around. Right? Well, with a binary number, we get the same effect by multiplying by a power of 2. And that's what we're doing here. Right? So this exponent part, in a sense, it kind of determines the scale of the number. Right? All that part of my formula is going to do is move the decimal around. Now the second part, the remaining 52 numbers, this is it's called the mantissa, or the significand, and it actually determines a binary fraction. Right? So for example, if I had 1, 0, 1, and then everything else was zeros, this would be 1/2 to the first power plus, let me put the 1 in here, plus 0 times 1/2 to the second power plus 1 times 1/2 to the third power plus zeros all the way down. Right, so this is a binary number that we're getting out of this part, but it's a decimal binary number. So we're normally, when we were converting to a decimal, we would do powers of 2. Here we're going to do powers of 1/2. Right, and that number f, that significand, is going down into here. And we're also going to do this piece here. We're going to take that significand and add 1 to it. And that really is kind of one of the neater tricks to this process. Right? The first thing that does is it means if we want to represent a number like 0.001, we don't have to waste any of our valuable 52 bits up here with leading zeros. Because I can just call this 0.000 when I add 1 to it, and then I'll for my exponent, I'll do this in powers of 10, because that's what everybody is more used to. This would be 10 to the negative third. Right? So I'm not wasting, again, any of those valuable numbers with leading zeros. And a second benefit to this is it adds a digit to this mantissa, right? And because I know that leading digit is always going to be a 1, I don't have to actually store it, right? So instead of getting 52 bits worth of precision, I get 53 bits worth of precision without having to skimp and try to move one of these exponent numbers over. Okay, so that 1 may seem a little weird at first, but it actually is really kind of a slick little thing to do here. Okay, so I know there's a lot going on there, right? A lot of moving parts here. In the next lecture, we're going to look at some specific examples of this and see how we can take some of these binary representations and actually convert them back into decimal numbers. Now there is one more definition that I want to mention here before we move on. Right, that is the idea of a normalized number system. A normalized number system is one where the leading digit of every number, except for 0 itself, is non-zero. So that's another thing that this 1 here accomplishes. Right? By putting a 1 out in front, I know that my first digit is not going to be 0. And remember, this f bit here is a decimal number. So that f thing is always going to be between 0 and 1. Right? We're going to talk very, very briefly about non-normalized numbers, really just in passing, right? But this is a phrase that you'll see, a term that you'll see come up, right? So you should know what it means. So I know there was a lot to digest on that last slide. So in the next lecture, we're going to look at some specific examples of these binary representations and see how to convert them back into decimal numbers. Now, this isn't something we're going to really need to do a lot of throughout the rest of this class, but being able to do these conversions is going to be important throughout the rest of this section in seeing what the limitations of this method are, right? And that is something that's going to affect the calculations that we do going forward.